Now, we will begin with what we call the contribution of certain scientists. Few seconds, please. Hello, mommy. Alex, class ti bẹ̀rẹ̀ ni ma. Okay. Bẹ́ẹ̀ ni mo observe ẹ ma. Okay, no problem. Only join inside. You can join. Okay, ma. Okay, no problem. Hello? Hello?
Yes, sir.
Yeah, sorry about that. Now, atomic structure is the focus of our discussion today. So there are a lot of stuff that we want to talk about under atomic structure. So we shall be discussing the contribution of scientists. Contributions of scientists. Can you see the screen? Hello? Let me change my Wi-Fi. Hello? Hello?
Hello, sir.
Can you see the screen now?
Yes, sir.
Yeah, so
Hello, sir.
contribution of scientists. I hope you can see clearly. So we want to look at some scientists and their contribution as far as the atomic structure is concerned. So we have a number of scientists who have actually contributed to the
Yes, sir.
discovery of the atomic structure. So they include number one, we have a scientist by name Democritus. He was actually a philosopher, not a scientist per se. Then we have J.J. Thomson. Please get yourself muted, please. We have J.J. Thomson. 3. We have John Dalton. 4. We have Ernest Rutherford. Right? We have R.A. Millikan. Okay? We have Henry Moseley. Number 7, we have James Chadwick. Number 8, we have, what was his name again? Neighbor. Then number 9, we have Heisenberg. So here we have some of the scientists who have actually contributed to the discovery of the atom. So we shall be discussing them one after the other. The first one in question is actually Democritus. So Democritus is actually not a scientist. He was just a philosopher, right? In, I think, about 500 BC. He made some propositions about an atom, and he was the first person to come up with the proposition that every existing composition is made up of atom. So the atom you are talking about here, to him, he called it atomos. And the word atomos simply means something that is divisible, that is indivisible, that is something that cannot be broken down. He presumed that when you take an existing entity and you continue to break it down, you will break it up to a point whereby it won't be breakable. So, and he called that part atomos, meaning an atom, something indivisible. But he was unable to support his preposition scientifically because he was just a philosopher. Years later, a number of scientists came up with prepositions and supported them with their theories. And the first scientist who came up with that was a scientist by name John Dalton. John Dalton. That was the first scientist who was able to come up with the proposition of explaining what an atom is and how they came up to be as a result of their theories. So we have the contribution of John Dalton. That's the first scientist to discuss. Are you listening?
Yes, sir.
Good. Now, what were the contribution of John Dalton? Number one, John Dalton is known as the father of atom. Because he was the first scientist who was able to propose an atom with some explanations, scientific explanations. So he was able to support his proposition using simple chemical reactions. So he's known as the father of atom. And another point you need to know about John Dalton is that he proposed some theories. We call it Dalton's atomic theory. Proposed 5 theories. So those theories are known as what? Dalton's atomic theory. There is a need for everyone to know this theory and to be able to list them in questions. Whenever it is required. So let me come down here and explain what I mean. Now, the theories, we call them Dalton's atomic theory. Everyone must be able to state that offhand. Do you have anyone that can try that? Number one, Dalton's atomic theory, the first one was that element is made up of small indivisible particle called atom. Can you hear me?
Yes, sir.
Now, this small entity is actually proposed to be indivisible or indestructible. Number two, the second proposition according to John Dalton is that atoms cannot be created nor destroyed. Are we together?
Yes,
The
sir.
third proposition or the third theory is that atoms of the same element are alike. and differ from atoms of other elements. Right? Now, the fourth one is that when atoms combine together, please, I hope you guys are noting something. You are noting what I'm doing. When atoms combine together,
Yes, sir.
Yes, sir.
okay, they do so in volume of simple ratio. Right? So when atoms combine together, they do so in volumes of simple ratio. Meaning, for example, when you have some constituent like hydrogen gas reacting with oxygen gas to give H2O, for example. Now, the combination will be done with simple ratio. When you balance the equation, 2 here, 2 here. So what this implies is that 2 volume of hydrogen react with 1 volume of oxygen to give us 2 volumes of water. Does that make sense? So the ratio of existence is a simple ratio. Is that clear? Now, this was the contribution that was made by John Dalton in explaining his theory, right? So,
So I thought there were
however,
five.
good. Number 5, I want you to go and find out number 5. I wanted to give you that. So, go and find out about what number 5 is. Number 5 is not a very common one, but go and find out about number 5. Now, these were the preposition that he made, and he used this preposition to explain the discovery of an atom. Now, after his demise, some other scientists came up and reviewed this theory. They observed that some of the things that he said were not very appropriate, so they decided to review it. So it came up with what we call the modification of Dalton's atomic theory. So it was then remodified. So we now want to look at the modification of Dalton's atomic theory. Few seconds, please. So we have modification of Dalton's atomic theory. So what are the modifications of Dalton atomic theory? The first one, can anyone tell me what the first theory was?
All matter is made up of small particles.
That are indivisible and indestructible, called atom, right?
Yes, sir.
Now it was modified. What was the modification? Right? The modification was that matter or whatever
All
elements,
matter is made up of small particles.
yeah, matter or elements. Okay, no, don't let me use that. Atoms, you know what was said before was that atoms are indivisible and indestructible particles. Elements are made up of indivisible and indestructible particles called atom, right? So now the modification was that it was later discovered that atom is actually divisible because atom contains some smaller particles. So it was modified to be atom are made up of subparticles. Are we listening? like proton, neutrons, and electrons. You get that? Hello? Can you hear me?
Yes, sir.
Okay. So that was the first modification of the theory, that an atom actually is something that can still be divisible, unlike the belief of John Dalton that, the belief of, John Dalton, that atoms are actually not divisible. So it was later modified that atoms are made up of smaller subparticles, which are protons, neutrons, and electrons. Number two, can you tell me what the second theory was, according to John Dalton? Anybody?
Atoms cannot be created nor be destroyed.
Yes. So if you look at that, atom cannot be created nor destroyed. It was modified that during a nuclear reaction, during nuclear reactions, right, atoms could be destroyed. Are you listening? So the statement of Dalton's atomic theory was only true for simple chemical reaction. You get the point? Are you there?
Yes, sir.
Yes, sir.
Do you understand what I mean?
Sir, please repeat the number 2.
Can you see the screen?
Yes, sir.
Somebody said
Yes,
I should
sir.
repeat number 2. Is it the theory or the modification?
From the modification from that bracket.
Okay. It, it was true. That means that statement was only true for simple chemical reaction. It's not true for nuclear reactions. So in nuclear reactions, atom can actually be destroyed because you can destroy the nucleus of an atom. Is that okay? Can I proceed?
Yes, sir.
Number 3. The third one is that atoms of the same element are exactly alike. This is also not true as a result of the discovery of isotopy. So what Dalton was saying is that atoms of the same element are alike, meaning that if you have atom of chlorine, it's always atom of chlorine. And the atom of chlorine is quite different from the atom of magnesium. Atom of sodium is different from the atom of neon. You get it? Now, it was later remodified that we can still have atoms of the same element that will not be exactly alike when isotopy was discovered. You get it? What is isotopy? Isotopy is a phenomenon exhibited by certain atoms possessing the same atomic number but different mass number due to the difference in the number of neutrons. For example, chlorine and chlorine, 1735 and 1737. Are we together? Now, these are chlorine with the same atomic number 17, but the mass number is actually different, 35 and 37. You get the point? So we say chlorine is undergoing isotopy. So the two isotopes of chlorine are chlorine 1735 and chlorine 1737. They are atoms of the same element, but they are not exactly alike. Do you get it? Do you understand?
Yes, sir.
Yes, sir.
So we can invariably say, so state the modification here. Let me clean this part. Okay. Now, the modification of that would be that isotopes of elements possess same atomic number but what? Different atomic masses. So, atoms of the same element might not be exactly alike. Exactly alike. Does that make sense? Do you get that?
Yes, sir.
Yes, sir.
Now, number 4. Who can tell me the fourth point?
A simple ratio.
Yes, when atoms combine together, they do so in volumes of simple ratio. Now, to modify that, this is only true for simple chemical reaction,
Sir,
right?
your screen is not showing.
Oh, few seconds, please. Is it showing now?
No, sir. Yes, sir, already showing.
Okay. So isotope of element, okay, now the fourth one, just like you said, when atoms combine together, they do so in volumes of simple ratio. So that was also modified, that this is only true for simple chemical reactions. We can have complex organic reactions whereby you have thousands of molecules combining together, right? Not in simple ratio. And this is very common to formation of polymers, either natural polymers or synthetic polymers. So in the formation of polymers, you have repeated number of monomers coming up together. They can be in hundreds, they can be in thousands. In fact, some can be in millions. They join together to form a final considered polymer. You understand? So in that situation, the ratio of interaction is not simple. It is what? Complex. You got the point? So how do we remove?
Sir, please come.
You said?
Sir, please come again. I
Now,
don't get it.
okay, let me explain that. It's quite easy. Now, you know, what was proposed by John Dalton was that whenever atoms are combining together to form products, they always combine in simple ratio, right? Now, that statement was only confirmed to be true for simple chemical reaction. We can have complex organic reactions like formation of polymers, either synthetic polymers or or natural polymers. An example of a polymer is carbohydrates. Okay? Carbohydrate is formed as a result of repeated units of simple sugar in their hundreds and in their thousands. They combine together to form a unit of carbohydrate. Are you together? Now, this combination is not a simple ratio combination. So, it implies that the statement that was given by John Dalton about the combination of atoms to be in simple ratio is not the case for all reactions. You get the point? There are some reactions whose combination of atoms are not in simple ratio, like organic reactions, formation of polymers. You get that? Is that understood?
Yes.
Yes, sir.
Okay,
Yes,
so
sir.
to remodify that, we say organic reactions right, involving formation of polymers are not in simple ratio combination. So that's the summary of Dalton's atomic theory and its modifications. Is that okay? Can I proceed? Hello?
Sir, what of the
Yes,
fifth
sir.
one?
I have told you to go and find out about the fifth one. I think I said that, isn't it?
Okay, sir.
Yes, go and find out. I'll ask you in the next class and you tell me if there is a possible modification for it. Okay? Now, number 5. Okay, sorry. Let me create. Few seconds, please. I'm trying to make a page. I don't know why this is clicking me back. Okay, let me go up. Now, that was the contribution of John Dalton. So we are supposed to know what was his contribution in terms of the discovery of an atom. So the next one we would like to discuss is another scientist by name J.J. Thomson. Are we listening?
Yes, sir.
So let's look at J.J. Thomson now and his contribution to atom discovery. Now, J.J. Thomson. Number 1, he was the one who discovered the electron using he discovered the electron using what we call the discharge cathode ray tube. Number 2, he discovered what we call the charge to mass ratio. Charge to mass ratio of electron. So that is represented as E over m. That's called charge to mass ratio. Is that clear? Number 3. It was also the same person that discovered what we call the pudding atomic model. Of pudding atomic model. Let's put it that way. Yeah. I hope you are together.
Yes, sir.
Okay. So, J.J. Thomson alone was able to do the whole of this, and there is a need for us to explain some of his discoveries. Now, he discovered the electron using the cathode ray tube. So, what did he do? He got a cathode ray tube. This is the tube. The tube looks like this. Now, it's like a glass tube. Then he inserted some electrodes inside him here. So, this was the cathode electrode, and this was the anode electrode. Are you listening? Then he connected it together, right, at a very high potential difference. So the voltage was very high, high voltage. Are you listening? And then this part is a vacuum pump. It is used to what? To remove air from this particular tube. So, and to increase pressure. So, actually, this was a vacuum pump. In here, there were spaces of air. We have some special type of air inside. And then he applied high pressure at a high potential with a high potential difference. Am I communicating? So when he did that, he observed something. What was his observation? So he observed that light was actually emanating from the cathode electrode. And that light was moving towards this direction of the anode. Am I communicating?
Yes, sir.
Now, the light that was emanating from the cathode, he called the light cathode ray. And that cathode ray was actually the electron. How did he conclude that it was an electron? He placed magnetic field in between the lights. So we have magnetic field here. I hope you are listening. This was positive and this was negative. Please, are you listening to my explanation?
Yes, sir.
Now, J.J. Thomson discovered that the light, when it was coming, it deflected towards the negative end of the magnetic field. So because it was deflecting towards the negative end of the magnetic field, he concluded that that ray of light was negatively charged. So the ray of light being negatively charged implies that that ray of light has a negative charge, which they concluded is now electron. Do you get the logic? Another thing that he discovered during his experiment using the cathode ray tube was that the ray of light, which is the cathode ray, possessed what we called a kinetic energy. It possessed kinetic energy because it was able to rotate a mechanical paddle wheel. Do you know rotor? You know what we call that rotor? The one they use in cars. Not necessarily cars, but that thing looks like this. When you were small, if you connect it like this, I don't know, maybe they are still using it these days. If you connect it to a battery, right, this part will be moving, such that if you place something on top of this, it will be rolling, right? Are you listening?
Yes, sir.
Now, what he did was that he placed a mechanical paddle wheel over this cathode ray here. Let's assume this is the mechanical paddle wheel. Because the cathode ray possessed kinetic energy, it was making that mechanical paddle wheel to rotate. So the mechanical paddle wheel was moving, it was rotating. Am I communicating? So this implied that the cathode ray had what? Kinetic energy. Does that make sense? Hello?
Yes, sir.
Yes, sir.
Okay. Please, I want you to be responding so that I will know maybe you are following or not. So, what are the another thing he observed was that when he placed an opaque object to, around the path of the cathode ray, let's assume the cathode ray was passing this way in the what's it called, the tube, and he placed what we call an opaque object. An opaque object is any object that do not allow light to pass through. So he observed that the cathode ray, while it was passing over the opaque object, right, it was casting a shadow. Are we there? Now, the light was actually casting a shadow simply because that cathode ray was moving like rectilinear propagation of light. Rectilinear, that means straight line. Rectilinear light propagation. So whenever you hear the word rectilinear, what should come to your mind is that something that moves in a straight line, right? So those were his observations while he was trying to discover the electrons using the cathode ray experiment. Is that understood?
Yes, sir.
Yes, sir.
Now let me
Yes,
put
sir.
down those um, modifications. I said modifications. Those observations, I will just summarize them here now. So now here was the observation. Observation. What's this again? Cathode ray tube. Number one, the cathode emitted light called cathode ray. Number two, the ray emitted deflected to the negative end to the positive end of the magnetic field. Is that okay?
Yes, sir.
So, meaning the ray is negatively charged. So, it is called the what? Electron. Number 3. The ray possessed kinetic energy. Right, which rotates a mechanical paddle wheel. Are you there? It's just like the summary of what I've
Yes, sir.
discussed. Then, can anyone tell me another thing that was observed if you have truly following? Any other thing that was observed that I have not mentioned? I've mentioned 3 now. Do you remember any other one that I have not mentioned as part of the observation? Anybody? I actually talk about casting of shadows now. Nobody remember that.
Okay, sir. Okay, sir.
So, cast shadow. Number 4. The ray cast shadow when obstructed by an opaque object. Is that clear? So that's the summary of the observations of J.J. Thomson cathode ray experiment. Do you understand that?
Yes,
It
sir.
was the experiment that
Yes,
is
sir.
used in
Sir, please can you
detecting.
read number 3?
Number 3, the ray possessed kinetic energy which rotates a mechanical paddle wheel. So, because it has kinetic energy, it will make a paddle wheel to rotate, to move. You get that?
Yes, sir.
Now, apart from this that we have mentioned, another discovery that was done by J.J. Thomson, if you remember, what were the contribution of J.J. Thomson? Number 1, we said he discovered the electron using the word cathode ray experiment, isn't it?
Yes, sir.
If you go back to what if you are truly writing the note in the class. Number 2, we said he discovered the what? Charge to mass ratio, right? We also said that he discovered what we call, he proposed the Paulding atomic model. These were the 3 things that is very prominent to J.J. Thomson. Is that clear? So we have just finishing discussing his contribution as far as the discovery of the electron is in the cathode ray tube. You get that? Now,
Yes, sir.
we are going to briefly discuss his contribution as regards the charge to mass electron. I will just say that briefly. He discovered the charge to mass electron. But look at this. Let me share this with you. Everyone is supposed to have this book. I'm going to share it to the platform later with you. If you have the hard copy, fine. But if you don't have it, you can get it. This is Lamlad Chemistry. It's going to be very useful for our classes. Now you can see here. Can you see this? Can you see what I'm sharing now?
Yes, sir.
Can you see it, please? Hello?
Yes, sir.
Yes, I can
Okay,
see it.
fine. So you get to realize that all what I've explained is found here as part of the discussion of John Dalton, I mean J.J. Thomson, in terms of its discovery of electron. You have here moves in a straight line normal to the what cathode and can cast shadow of an object placed along their path. Can you see that? 2. Possess kinetic energy. I hope you can see what I'm pointing at. They possess kinetic energy and so can cause the motion of a mechanical paddle wheel. You can see that?
Yes, sir.
Then number 3, attract positive charge and repel negative charge, indicating that they are negatively charged. So then I talked about charge to mass ratio. Now you can put it in your notes that charge to mass ratio, right, is equal to, it is a constant value, and the value is 1.76 times 10 raised to the power of 11 coulombs per kilogram. This is charge to mass ratio. Can you see the value? 1.76 times 10 raised to the power 11 coulombs per kilogram. Is that clear?
Yes, sir.
Now, and lastly, on the contribution of John J.J. Thomson. Now, J.J. Thomson proposed what we call the pudding atomic model. Do you know pudding? Pudding is like a type of cake that is prominently used in the European world, either in UK or US. Let me show you how that cake looks like. Do you know the pudding cake? Anybody? For anyone who is used to cake, do you know what we call the pudding
No,
cake?
sir.
No.
No, sir.
Okay. Let me show you how it looks like. I hope you can see my browser.
Yes, sir.
Pudding cake. Let's look at images. Now, this is exactly what I want you to see. Few seconds. Particular about this one. It's still coming up. I don't know why it's taking time. Yeah. Okay, not this one per se. This is not what I clicked. I think this is
The
wasting
cake
my
will.
time. I think it's still loading. Yeah, this is exactly what I want. You can see this, right?
Yes, sir.
This is a special type of cake called the pudding cake. So Dalton was trying to propose how an atom looked like. So he said that an atom is like a sphere that is made up of positive charges in which negative charges are embedded. That was his proposition about um, an atom. That was his own model. His own model, how he viewed an atom. So let me draw that. Let me draw that so that you can see what I mean. So it's like this, like a sphere. Can you see the screen?
Yes, sir.
Made up of positive charges. Positive charges inside this, like this, right? And then you have negative charges embedded. Negative charges this way. Can you see that? This is what we call the pudding atomic model. It was propounded by who? Who propounded
J.
this, please?
J. Thompson.
Thank you, J.J. Thomson. He was the one who propounded this theory. And to his own belief, he believed that this is how an atom should look like. You get it? So later, after his demise, a number of scientists came up also to review this structure of an atom. Now, that is how Ernest Rutherford came into play. So we are going to talk about the contribution of Ernest Rutherford now. I've explained the contribution of how many scientists now? How many scientists did I talk about?
Two.
Two. John Dalton and J.J. Thompson.
Good. So we now
Yes.
want to talk about Rutherford. What was his own contribution?
So he proposed how an atom looked like.
Exactly.
J.J. Thompson.
Good. J.J. Thomson, Ernest Rutherford made a proposition of how an atoms look like. He used what we call the planetary model of atom. I think I need to explain this well so that you can understand what I mean. So, planetary model of atom, what's the meaning? The way we always write atom today, we draw the structure of an atom today, maybe in our chemistry class or what have you. So we draw it this way. Look at it. We say an atom is like this. It has something like this. You have something at the center, the nucleus, and then you now put electron. Abi? This way. Isn't it?
Yes, sir.
This structure was first proposed by Rutherford. Are we together? And we call it the planetary model of atoms. So you have contribution of Rutherford now. Number one, proposed the planetary model of atom. Now, how did this discovery came about? The discovery came about as a result of an experiment that was done by the student of Rutherford. Rutherford had two students. The name of the students were Geiger and Marsden. The name of these two students were Geiger and Marsden. Are we listening? Now, Geiger and Marsden were in their lab and they were making an experiment. The experiment they did was that they fired an alpha particle on a thin gold foil. They did what? They fired, that's Geiger and Marsden, fired what? An alpha particle over a thin gold foil. So let's assume this is the alpha particle. Please, am I communicating?
Yes, sir.
So we have an alpha particle this way. They now fired it over a thin gold foil. Let's say this is a gold foil. Gold foil. Now, then you have to use a monitoring screen. This screen helps to detect radiations. This is a screen. Now, what was observed? You observed that when they fire the alpha particle over this thin gold foil, are you listening? Most parts were moving sideways. They were passing over the thin gold foil, except for a very small portion that was deflecting sideways. Are you listening? Am I talking at all?
Yes, sir.
Yes,
So
sir.
when they did that and they observed that most of the alpha particles were moving, they were moving out of the thin gold foil, but just small particle, small part of it were deflecting sideways. And that fraction that was deflecting sideways were very minimal. They were detected by the screen, the recording screen. So this discovery was highly amazing to Geiger and Marsden. So they could not explain this phenomenon. It was like you firing a 1.5-inch bullet on a sheet of paper. Am I communicating? And that sheet of paper fires the
Yes,
bullet
sir.
back at you. It's like you are firing a 1.5-inch bullet on a tissue paper, and the tissue paper fires it back at you. You know, it is highly miraculous. So they could not explain this phenomenon because their understanding about an atom was that of the planet, but that of the Purdue atomic model. So they now took, Geiger and Marsden now took this discovery to their teacher, who was Rutherford. Then Rutherford now explained the possible consequence of this discovery, or how this can be explained. So he later concluded, that is, Rutherford concluded that for us to have a possible deflection sideways of this mineral, what's it called, alpha particle, it must have been that you have a positive concentrated center. You must have a center that is highly what? Concentrated. And then you have a large empty space. Are we getting it? Am I communicating?
Yes, sir.
Let me draw it. So the center is just like this, with a large empty space. So it implies that that large empty space is where the most of the alpha particles were passing. You get the point? And the tiny deflection that was observed must have been that it was hitting the heavy concentrated center that was deflecting it backward. Do you get the point?
Yes, sir.
So it means that most of the alpha particles were passing through, and while very minimal parts were actually getting deflected. So this led to the discovery, or the planetary model inception. So which implies that an atom is made up of a heavy concentrated nucleus and surrounded with a large empty space. Right? So an atom is made up of a what? Heavy concentrated nucleus with a what? Large empty space around it. You get that?
Yes, sir.
Good. So that was the contribution of Rutherford. Rutherford discovered the planetary model of atom with this experiment. I hope you understand, because all these details are important, because they are the things that are to be covered in the scheme. You get my point? These are places where they will be bringing questions from. So it's important that you pay attention to these details. Is it clear? Hello?
Yes, sir.
Okay.
Yes, sir.
Now,
Yes, sir.
Yes, sir.
in our sorry. Ah,
Mommy too is in the class. Oh.
I was like, I had a different voice.
Mommy,
So
I
all
don't
this
share any. Mommy. Alaikum salam.
it's okay. So, how many scientists have we discussed now?
3.
What are they?
Yes.
3.
Doubt,
Rutherford, J.J. Thompson, and John Dalton.
Good.
and
So
Kinney
these are
Trafford.
Yes, sir.
Trafford.
these are the scientists that we have discussed so far. We have many more to discuss for today. So, but those ones will not give us so much explanation like we've done. The next one is the contribution that was made by Nebor. Okay, so what was the contribution of Nebor? Nebor actually talked about quantized energy of electrons. What is the meaning of quantized? Quantized means fixed. So Nebor was of the opinion that Rutherford didn't talk about anything about the electron. He only talked about empty space. But Nebor was now of the opinion that these electrons are actually in a fixed position. That if you have an atom this way, and then you have the center of the nucleus this way, so around it you are going to have some positions where electrons could be found. So an electron can be found here. This is the fixed position of this electron. An electron can be found here. This is another fixed position of the electron. An electron can also be found here, which is another fixed position of electron. This is called the quantized energy theory. What do I call it? Quantized
Energy theory.
Yes. Now, however, the explanation that was given by Nebor about this was only true for one electron system. So this was only true for one electron system. So what do we mean by one electron system? An example of one electron system is hydrogen atom, because hydrogen has just one electron, so that would be one. You get it? So Nebor explanation about the quantized energy theory cannot be verified using multi-electron system. Are you getting my point? That electron has a fixed position, that this is a particular position where you can find electron. That theory is actually certain or was proven true for just one electron system, like hydrogen. Are you getting my point? It was found not to be true for multi-electron system, like helium, lithium, beryllium, boron, or what have you. So any atom that has more than one electron cannot be used to prove the theory that has been proposed by Nebor, that electron has a quantized energy. You get my point? Do you understand?
Yes, sir.
Good. Now, as a result of that, he proposed, that is, Nebor proposed that in a one electron system, let's assume that we have an electron here. This is where the position of the electron is fixed here, right? Now, if this electron acquires energy, right, it's going to be excited, meaning it's going to move from this lower energy to a higher energy. So it's going to be excited. Now, it can be excited to this position. Are you getting my point? Now, when it gets to this position,
Yes, sir.
the electron, anything that goes up must surely come down, isn't it? So when it is excited, it is at a very high position. So the electron will want to come back down. So as it is coming back down, it's going to come down with emission of light. Are we there? And that light will be of a particular wavelength. So it is coming down with a particular wavelength of light. So, and because of that, Neighbor proposed that that electron was in a fixed position. Am I communicating?
Yes, sir.
Yes, sir.
So that was the proposition or the contribution of Neighbor. Neighbor actually talked about the quantized energy of electron, which was only true for what? One electron system. It is not true for what? Multiple electron system. Quantized energy means what? Fixed energy. That electrons are often found in a fixed position. They are quantized. So that is why you talk about the K shell, the L shell, and the what? M shell. You get the point? So another contribution, another scientist that we are going to talk about again is James Chadwick. Let me go up here. Talk about James Chadwick. 2 seconds, please. Why did I call the name of the scientist again?
James Chadwick.
Yes,
Chadwick.
James Chadwick. James Chadwick. What is the contribution of James Chadwick? James Chadwick discovered the neutron. In the year 1932. And the neutron was the last subparticle to be discovered. Are we together? So, nothing much about James Chadwick. That was his own contribution. Then you have Henry Moseley. What's the contribution of Henry Moseley? He discovered the atomic number. Are we there?
Yes, sir.
Then again, we have another scientist by name R.A. Millikan. What did I call his name?
R. A. Milligan.
Millikan.
Millikan. K. R.A. Millikan. R.A. Millikan. What did he do? He discovered the charge on electron using the oil drop experiment. He discovered the charge on electron using what? Oil drop experiment. Does that make sense?
Yes,
Now,
sir.
let me tell you the values quickly. Now, the value of, you see it here. Let me show you this. So, you have R.A. Millikan here. Now, this is the value for the charge on electron. So, 1.6 times 10 raised to the power of 19 coulombs. Put that down. Charge on electron is 1.6 times 10 to the power of minus 19 coulombs. Are we there? Have you written that?
Yes, sir.
Then we also have
So,
mass of electron. The mass of electron is 9.11 times 10 to the power of minus 31 kilogram. Nine point 11 times 10 to the power of minus 31 kilogram.
So these values are for what?
Values of the mass of electron, charge of electron, and charge to mass ratio. We said the charge to mass ratio. I've given you the value for the charge to mass ratio before. 1.76 times 10 to the power of 11, right? Are we there?
Yes, sir.
Okay, fine. So let me go back. I think I've mentioned a Millikan. So the next scientist we are going to talk about is Heisenberg. Is what? Heisenberg. Say that, everybody. Say Heisenberg.
Heisenberg.
Zimbabwe.
Yes. So he proposed what we call the Heisenberg uncertainty principle. So let me preview that. We have the duality nature of atom, de Broglie. So, but that is not necessary for now. But Heisenberg, I think I need to talk about it. So this is Heisenberg. Heisenberg. So what did he propose? He proposed the uncertainty principle. So what is this principle all about? The principle is telling us that you cannot detect both the position and the momentum of an electron in an atom simultaneously. Let's assume this is an atom, right? And you want to locate the position of this atom. Let's assume this is the electron here, right? Let me say it somewhere around. Can you hear me?
Yes, sir.
Now, Heisenberg is telling us that it is not possible for you to know the exact position of this electron and also know the what? The momentum. So, it's either you know the position and you do not know the momentum, or you know the momentum and you don't know the position. You get the point? So, Heisenberg's uncertainty principle states that both momentum and position of electron cannot be determined simultaneously. Is it clear? So we have P dot x is greater than or equals to h over 4 pi. So this is like the equation for Heisenberg. So where the change in P stands for change in momentum and change in position greater than or equals to h over 4p. You don't necessarily need this. What you just need to understand is what? This principle. Is that understood?
So,
Now, that's it. So we are done with the contribution of these scientists. So these are the few ones we need to do, and I believe you understand them properly. Now, before we move ahead, I need to ask you some questions. Okay? So I'll be calling your names one after the other, then you give me answers. And I don't want it to be either you tell me the answer, or you forget about it. So the first question goes to Hussein. Are you there, Hussein?
Yes, sir.
Okay. Now, Hussein, What name two contributions that was done by J.J. Thomson as
He,
far as an atom is concerned?
he discovered electron using cathode ray tube.
One.
He discovered charge to mass ratio of
God
electrons.
bless you. Thank you. Olamide, are you there?
Yes, sir.
Your question. Which scientist discovered the neutron? And which scientist discovered the charge to mass ratio?
The Charles Thomas ratio was discovered by J.J. Thomson, and the neutron was discovered by James Chadwick.
Very correct. God bless you. Mashallah. Okay. Dean, are you there?
Yes, sir.
Your question. What is the name of the scientist that proposed the planetary model of atom and briefly explain his discovery? First, what is the name of that scientist that talked about the planetary model of atom? That's the first question.
Rutherford.
Rutherford, correct. Can you explain briefly how this experiment came, how the discovery came by?
He used an alpha particle and a gold foil.
Good.
Then, as he was sending the alpha particle towards the gold foil, most of the particles were moving out of the gold foil and some were deflected
Thank you. God bless you. What was then
after
his
viewing them
conclusion?
from the screen.
Good. What was then his conclusion? You are right. I just want to get the conclusion. After that experiment was done and he observed that, so what was his conclusion? Let me help you. The conclusion is that an atom is made up of a heavy what? Nucleus. Right? Surrounded by a large empty space. You get that?
Yes, sir.
Yes, that was his conclusion. Now, that is the end about the contribution. We are going to look at some questions later, but before we move to the end, because I have about 2 minutes to end the class, I want to ask everybody, do you all know the first 30 elements?
Yes, sir.
Yes, sir.
I did not say the first 20 elements. I said the first 30 elements.
Yes, sir.
Good. So if you know the first 30 elements, you are going to make my work easy, the next class easy. Because in the next class, we'll be working on things surrounding what? Electronic configuration. Okay? Now, I'm going to ask simple questions. I will call your name, you give me the answer. On the first 20 elements first. Okay? Are we ready?
Yes, sir.
Good. Hussein,
Okay, sir.
are you there? Hussein, are you with us?
Yes, sir.
Okay, fine. Now, which element has, what is the name of the element that has atomic number 16? Don't check AIO.
Sulfur.
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 Somebody said that before. If I do not direct the question to you, don't say it to.
So I said sulfur. I was
Oh,
reading it. That was Time.
Okay, okay. Sulfur, correct. Correct. Now, Olamide, what is the
Yes, sir.
atomic number of magnesium?
Magnesium is 12, sir.
12, very correct. Dean, what is the
Sir,
symbol of calcium?
Ca.
Ca, correct. Good. So in the next class, we are going to look at everything surrounding electronic configuration, right? SPDF, rules that we use in filling electrons and so on and so forth. So do you have any question for today?
No,
Anybody
sir.
with question?
No, sir.
No question. So if there are no questions, inshallah.